Hi everyone, welcome to This Week in Space Science, another exciting show about space science. This is Sean Cruzen, my partner here on this show, Twiss as we call it, coming to you from Columbus State Television at Columbus State University in Columbus, Georgia. That was 3 Columbuses right there in a row. I'm glad to have you here. Sir, how are you doing today?
I'm very well, Mike. Thanks. Thanks for having me on the show again today.
Well, it's your show, so what we're doing is asking you the questions, you provide the answers, and we've been doing this for quite a while. We're informing people about what's going on in space, what's on planet Earth that is connected to the space industry, and
that's right.
All of those things out in the universe, and we've covered so many things, black holes, dark energy. It goes on and on.
Lots of fun stuff.
I mean, we're constantly learning something about it. Now, I know today on this show, we're going to talk about solar flares. We've got a big flare story.
Yeah, there's a flare story.
Say that. And then a little bit later on, you're going to talk about an asteroid?
That's right. A very unusual asteroid or minor planet out there.
You know,
in our solar system.
In our solar system. I get a little nervous when you start talking about these asteroids, because it seems to be there's always a story in the paper or on the media how close one came to us, you know, and we need to be prepared, vigilant. I'm not sure what we do if we find one coming directly toward us yet. I hope we have a plan. But maybe this is an interesting story, maybe not a Earth-threatening type of story.
This is an asteroid story that has a happy ending. It's safe.
Oh, I love it.
So, but we'll get to that in a minute. Because
so it's a feel-good story.
Before I tell you the feel-good story with a happy ending, I've got to tell you a scary story. Well, it has a happy ending, but it's still a cautionary tale. So
okay, we're
going to go there first.
We can cover it. You go ahead and start. So I think you're going to start talking about a flare.
A flare, yep,
right,
a giant flare that occurred. So first of all, before we begin jumping right into the apex of the topic, what we want to do is kind of set it up a little bit and just remind people about some of the phenomenon that can take place on the sun. And then there have been other shows on the same topic that we've done. In fact, if you're pulling this up through the archive, I would point you back to last July 2013, where we did a show about solar maximum, solar minimum, and the fact that the solar maximum that we happen to be involved with right now is kind of a little bit of a rare one because it's kind of quiet. But before we do that, let's talk about what this means. Okay, so here's what happens. The sun it's a big ball of plasma. It actually, because it's not solid, it's plasma, it rotates faster in the middle than it does at the poles. And as it's rotating faster in the middle, it drags its own magnetic field around, and that magnetic field gets wound up. And so it winds up for a number of years, and then it reaches this point where it's the most wound up that it can be. During that time, that's where you would see the most sunspots, the most solar flares would occur, these giant explosions from the surface of the sun, and we call that period solar maximum. We're in that period right now. We're at solar max right here when the show's being recorded, 2014. Now, what then happens is that field gets so contorted and messed up that it literally breaks down, and then it reforms with the poles in the opposite orientation. Now, I don't mean the sun flips over, but I mean the actual magnetic field breaks down, and the magnetic field poles reverse polarity. And so what was a north magnetic pole becomes south, what was south magnetic pole becomes north, and then the whole field is a nice stable configuration, and then it winds up again. That whole period between one solar max and the next is about 11 years. And I think we have a picture here which shows the sun taking its solar maximum and another picture of the sun taking its solar minimum, and you can really tell the difference between these two images, because what you're going to see is you're going to see the sun at solar maximum. It's got sunspots all over it. Here we see it on the left-hand side, and you can see that those sunspots have kind of gathered toward the equator of the sun. Those big dark spots, we call them freckles sometimes, just joking around with the kids that visit our center. But when you see those freckles on the sun, those are giant solar storms. They are contortions in the magnetic field of the sun. They're caused by this winding that I just described. And when those magnetic fields get very bent, it causes the convection to slow down in certain surface areas on the sun, and those spots cool off. And so that's why you get these big dark spots on the surface of the sun.
So the darker the spot, the cooler that may be.
That's right. So when you see these variations in brightness on the surface of the sun, what you're really looking at are variations in temperature. And so those dark spots are cooler than the bright surface around them. So that's a temperature variation that you see on the surface of the sun there. Okay. Now, if you happen to notice that right-hand side photo, you saw almost no sunspots at all, because that was a photograph of the sun taken at solar minimum. So that's at a time where the field is very stable, the poles are stable, and you don't have all this activity. Well, right now we are at solar maximum. But again, if you review that show that we did back in July, you'll find out that we talked about the fact that we're at a relatively quiet solar maximum. So of the solar maximums that we've recorded over the history of science and our history of monitoring the sun, this one happens to be not as active, not as many big sunspot groups, not as many big solar flares.
Okay, and now, that could be a good thing for us.
It can be a good thing, because with each flare that occurs facing at the Earth, you're liable to have all kinds of different effects. And so when a giant flare erupts, it sends out all kinds of material shooting at the Earth, and as that material shoots at the Earth, it's charged radiation from the sun. And that can be very damaging for both the biological life forms on the surface of the Earth, like us, or our electronic telecommunication systems, because it's just a wave of electricity running into the Earth. And so when you have that wave of electricity running into the Earth, you can actually affect the Earth's power grids, power lines, television, radio communication systems, and the like. And so I mentioned biological systems a moment ago. I don't want to get people too nervous.
No.
We have a magnetic field around our Earth that's generated by the Earth itself,
yes,
and that does a good job of shielding from most of the sun's radiation.
Right.
As long as those flares aren't the most powerful flares, we don't really receive a whole lot of the effects of direct radiation here on the Earth because of that magnetic shielding caused by the Earth's own magnetic
field. And if we didn't
field.
have that, we would be in trouble, I understand. Those
That's
flares
exactly
and all
right.
of that activity would come right to us. Okay.
It would indeed. And so a case like that you just described is if astronauts were on the moon at the time of one of these giant solar flares. And of course, there were astronauts on the moon. It just happened to be a time where there weren't all that many flares going on. But had those astronauts been walking on the surface of the moon when one of the larger solar flares would come, the moon has no magnetic field, so it wouldn't be able to protect those astronauts in that way, and they would be in the direct path of this radiation, and they would receive lethal doses of radiation to their bodies. And so when we talk about the future of space exploration and about sending astronauts to a place like Mars, we have to understand that while they're in transit, and even on the surface of Mars, which doesn't have much magnetic field either, that they are exposed to these potential storms from the sun, which can do a whole lot of damage because they have radiation. And so this is one of the concerns that we have, and so we have to think through these processes. All right, so here's the thing though. There was another solar maximum back in the year of 1859 that was also relatively quiet. In other words, there weren't a whole lot of sunspots on the sun at that time, and even though it was solar maximum, we didn't have as many solar flares going off, there weren't as many bright aurora, which are these northern light phenomenons that are associated with large solar flares. So the interesting thing though was, during that period of quiet, there was one of the most massive solar flares ever recorded that was triggered during that relatively quiet solar max. It's now called the Carrington event, or some people know it as the Great Solar Storm of 1859. The eruption occurred directly at the Earth. The radiation from that flare was so intense that it actually got through the Earth's magnetic field fairly substantially. And because it did that, it actually affected the technology of the day. Now you might think, right. What was the technology of the day in 1859? Right. So
it would have been telegraph poles, maybe.
Exactly. So the communication system of the time were telegraph lines, right? And so there was so much radiation that came in from that solar storm in 1859 that it overloaded the telegraph system, put so much charge on the wire that it actually set both the telegraph wires on fire and the receiving stations at the end of those telegraph lines. It was just an overdose of charge from the sun during one of these giant eruptions. And so that was very bad for those people at the time, right? Basically their telegraph systems were either overloaded for a short period of time or they were destroyed for a longer period of time. And,
Right.
and the honest truth is, Mike, that there just wasn't as much technology back then. And so people have asked the question, what would happen if a similar event occurred today?
Oh, you can already guess that we are connected in so many ways. All the satellites circling the Earth, our communication, our cell phones,
Yes,
our
exactly.
satellite images. I mean, all of the things television, on and on and on.
Even
electronic
more
banking,
fundamentally,
maybe. I mean, a number of them.
if you add in how connected we are and how dependent we are on the power grid,
Yes.
and electricity. So if you even just think about electricity, certainly all those other communications devices and other pieces of high technology, they're also connected to the power grid, right? But just the fundamental kinds of things that you think the power grid is necessary for.
Right.
If you look at areas that have had natural disasters, fairly major natural disasters, that have cut people off from power for any substantial amount of time, a lot of times when they're without power, they're also without clean water, right? And so,
Yes.
so it cuts right to the fundamentals of human need, especially in large urban areas, when you take away the power grid and you take away technology, right?
Right.
And so there's actually a phrase that's coined by social scientists. It's called social vulnerability. And they actually they can analyze geographic regions of our country based on what's known as social vulnerability. How vulnerable is that society to some kind of catastrophic event that would take out the modern conveniences and technology and access to modern infrastructure that we enjoy in our daily lives?
Well, we're also so dependent on it too. I mean, like you were just saying, but we take it for granted.
Yep.
So interruption in that service, it could be devastating.
It could be.
Well, certainly inconvenient if it's a low level, but devastating in other ways.
And we know some of this stuff already by just looking at what happens during a hurricane or a particularly severe outbreak of tornadoes or things like that. We already know that very bad things can take place if people are cut off from power and from technology for short periods of time. Well, the American Academy of Sciences actually went in and studied the Carrington event of 1859.
Okay.
And said, the premise was this: if that same event were to occur today, how bad would it really be? I mean, how much danger are we really in? And so some of the numbers that came out of that study were very interesting.
I bet.
And one of those numbers is the Carrington event, if it occurred today, would it cost at least $2 trillion of damage in the United States alone. $2 trillion. To give you some perspective on that, that's about 20 times the amount of damage done by Hurricane Katrina. So when you think about 20 Hurricane Katrinas all occurring at the same time, and obviously the kind of damage is not the same, but just the cost amount for that damage being 20 times what Katrina was, that's really devastating to our country. Here's the thing I find equally interesting and perhaps a little frightening. That flare, that 1859 flare, if it occurred today, would damage our power grid in such a way that it might actually take years to replace all the components of the power grid. So people might be without power for years. And that's really, that's an interesting thought process, right? So, so if you suffer so much damage to the power grid of the United States that the whole grid at least wouldn't be restored up to its current capability for years to come, that means people are going to be without power for extended periods of time. And that's a frightening
That is frightening, as a matter of fact. Well, I mean, it has occurred.
Right.
So there is a possibility, we cannot rule it out, that this will occur again.
That's exactly right. And so that brings us now to the apex of the story.
All right, here we go.
Which is
serving it up there.
There was a new study that was just released in what they call Nature. It's the journal Nature, but it's their communications. So Nature Communications, which are it's an expedited process to get it through the review process for a journal. And the reason they do that is because the story is so important. So scientists have actually studied a flare that occurred in 2012. July 23rd, 2012, there was a mega flare that occurred, also a second one. And it was the combined output of these two flares occurring simultaneously within minutes of each other, about 15 minutes of one another, on July 23rd, 2012, that shock wave that expanded out away from the sun on that day was just as powerful as the Carrington event.
Okay.
And so this is had some analysis to it, and you might say, well, okay, well, nothing happened. Well, here's the thing. That event was not Earth directed.
Okay.
It shot off in a different direction.
All right, good.
So the only reason we didn't suffer a Carrington-like event in the modern era back in 2012 is because that set of flares happened to shoot off geometrically in a different direction. And when you might ask, okay, well, how do we even know then that the flares were that powerful? Because one of our satellites was out there measuring that event from the sun. So we have these two suns that are called the stereo satellites. I said suns. We have these two satellites that are called the stereo satellites that are monitoring the sun. And when we are on one side of the sun, these two satellites are on the other side of the sun, and they're separated by a distance so they can monitor the sun literally in stereo, so they can measure the three-dimensional effects of features that are shooting off the face of the sun. And so these two spacecraft monitor the sun all the time, orbiting the sun in the same orbit we do, but on the opposite side of the sun from our Earth. Well, this flare shot off and impacted one of those two satellites. Okay. And so that satellite was able to take some very accurate measurements that let us know just how intense that flare was. And it was actually on par with the Carrington event. So here we are at a period of relative quiet, a quiet solar maximum, but a quiet one. And we speculated back in July right on this show, because other scientists had already speculated this. I was just reporting on this. But scientists had speculated that, you know, it's sometimes during these quiet events that you get these mega flares to occur. And guess what happened? A mega flare actually occurred, and one of our satellites was there to measure it. So
man, we got lucky it wasn't aimed at us.
That's the lesson.
That is the issue.
The lesson is society really needs to be better prepared for a big solar event like the Carrington event, because they can occur. And we just saw it, we just missed because of geometry, one occurring in 2012.
Well, I don't know how we prepare for that. I mean, that's the sun doing its thing, and if it aims at us, and we've got this magnetic field, we hope that that's going to hold up. But as you just described a few minutes ago, it's going to be devastating if it's directly aimed at us.
Exactly. The Earth's magnetic field, as good as a shield as it is, it's still an insufficient shield to ward off the effects of one of these mega flares. So what a lot of solar scientists are suggesting, and space weather forecasters, space weather is the interaction between all this material from the sun and the Earth. That's what we call space weather. So there are actually space weather forecasters, people who spend their time talking about how the sun's environment will be affecting the Earth on any given day. What a lot of these people are recommending is the same thing that a lot of weather experts also recommend, which is be prepared. Have a preparedness kit. If you look at a natural disaster that might take out your power and your water for an extended period of time, you need to be prepared. And you might think, well, I don't live anywhere near any place where hurricanes happen. And yeah, we get a blizzard or two, or maybe we get a tornado, which affects a narrow band, but I don't really need to be prepared for those mega disasters because I'm a long way from the seacoast and I'm in a place where earthquakes don't really happen. So I don't spend a whole lot of time stocking up on flashlight batteries and having a preparedness kit. Well, it turns out that there's one more natural disaster that the solar scientists are recommending that you think about, and that is a giant solar flare that could take out power and water and the essentials of your daily life for an extended period of time, and you need to be at least ready on some local level yourself for that kind of event. And then also government officials also need to be thinking and preparing, you know, our things like our power grids for a redundant backup system or something that can be quickly put in place to replace at least the fundamentals of the power grid.
And they need to. And then I mean, how can you protect that? Is it lead? Does lead shield work? I mean, what is it that you do to protect those huge government and those grids that we were talking about?
And you know, there are precautions that you can take on the grids themselves, but one of the other things you have to have is you have to have a plan in place to where if something like this hit, you would have the components necessary and the personnel necessary to quickly repair the power grid. And so I think the backup plans really are more along the lines of, yes, some protection to the existing grid, but also have a plan in place to be able to mobilize very quickly and replace the power grid that if it went down due to one of these large storms. And that's no mean feat. That's no easy task. Right? So I think solar scientists are probably very aware of what they're asking the government to prepare for. However, they're saying, hey, look, it really can occur. It did occur in 1859. It did occur in 2012. It just went in the opposite direction. So just be aware. Be aware that this is a real possibility that cities and municipalities and our country itself might face because of the sun. And I think a lot of times people don't think about the sun being in that threat group.
No, we don't. But you have just brought us a particular amount of awareness about those kind of things. And I'm wondering, so if it's the difference, 2012, you said the one that missed us, the other one was 1859, is that right?
That's right.
All right, so that's a time span right there. I guess we need to calculate that just a little bit. All right, Sean, thank you so much for bringing us that story right there. That was important and scary at the same time. And I hope the next story has a little less danger with it.
There's practically no danger whatsoever.
It's an asteroid, but I never, you know,
I mean, as you mentioned at the first of the show, asteroids themselves can be dangerous because we have these near-Earth asteroids or Earth-crossing asteroids, but this isn't one of those. Okay. So we're just going to have fun now and talk about fun, happy things in the world of science. And we're going to talk about a particular kind of asteroid, which is called a Centaur asteroid. So here we have some asteroids in space. These asteroids happen to be Trojan asteroids. These Trojan asteroids are in the orbit of Jupiter. And so, I put this slide in here to say, hey, people think about the asteroid belt, which is between Jupiter and Mars. Sure. But there are other groups of asteroids out there that are not in the asteroid belt. And so we have the main belt asteroids, but then we also have these asteroids, which are called Trojan asteroids, which, if you know anything about this weird concept in physics called a Lagrange point, they're stable points in the orbit of a planet around the sun, where objects can sit there and hang there either ahead of the orbit of the planet or behind the orbit of the planet. In this case, it's both. And you saw those two groups of rocks, both ahead of Jupiter and behind Jupiter. Those are what's known as the Trojans, and they orbit the sun with Jupiter. Now, there's another group of asteroids out there that we call the Centaurs. And I've got a map of some asteroids here. It's actually kind of a plot. And there's multiple dot colors on here. I'll try to explain those to you. All right. So you see the green objects. You see the pink objects down in close to where we see the sun right in the middle. You notice that Jupiter sits in the middle of those pink ones. Well, that's because the pink ones are those Trojan asteroids that I was just talking to you about. Yes. And they're in the orbit of Jupiter. You see the green ones out there, they're well beyond the orbit of Neptune. We call those the inner Kuiper belt objects, and Kuiper belt is the objects that are out there by Pluto. Essentially, Pluto is a kind of Kuiper belt object out there beyond Neptune. Now, if you look in between, if you look between the green ones and the pink ones, you're going to see some orange dots in there. Okay. The orange dots are a group of asteroids that mingle themselves in and amongst the gas giant planets. And so those orange dots we find in the neighborhood of the large planets Neptune, Uranus, Jupiter, Saturn, in the region of the gas giants. So those are the ones that are called the Centaurs. And so the Centaur asteroids occupy that region in our solar system. The asteroid that we're going to be talking about today is one of those Centaur asteroids, and its name is Chariklo. Chariklo is an asteroid that's a Centaur that when it did something very interesting here a little while back. Chariklo, one of the Centaurs, passed between the Earth and a distant star. So if you imagine a distant star out here and you're observing this distant star from the planet Earth, some of those asteroids, because they're further from the sun than we are, they can pass in between that distant star and you. And when they do, they can, if they line up just right, which they only rarely do this, but if they line up just right, they can have what's called an occultation. In other words, they block out the light from that distant star, and to your eyes, that starlight flickers just a little bit. The star appears to dim out for a little while and then come back. Well, when you have one of those occultation events, you can actually tell some things about that asteroid. So scientists are very interested. How long the starlight flickers out tells about the size and the speed and the shape of the asteroid. And so it's an interesting time to do science on an asteroid. Okay, so the story about Chariklo is scientists were watching this star. They knew the asteroid was going to pass by. But before the asteroid got there, the star flickered a little bit. Then the asteroid passed by. Then the star flickered again a little bit. And scientists said, well, why did that happen?
Wait, there's something else
There's
going on.
something else going on.
Right,
And in particular, there were a group of scientists who were Brazilian astronomers. They're from the National Observatory in Rio de Janeiro. And Felipe Braga Ribas was the head scientist on that team that watched this event occur where that asteroid passed in front of the sun, or in front of a distant star, and the distant star's light flickered a little bit. He caught the preliminary flickers and the post flickers as well. It turns out that the pattern ahead of time was the same as the pattern afterwards, except flipped, reversed in time. And from that data set, he was able to determine that there were rings around that asteroid. So this is just a very interesting way to do science, first of all. It's a very interesting kind of event that they were able to measure, but it led to an important conclusion. There's an asteroid out there that has rings around it. It's rings like Saturn's rings.
I don't think I've ever heard of that before.
No one's ever heard of that
before.
before.
About planets. We're happy with Saturn and Neptune and so forth, but an asteroid with a ring.
An asteroid with rings. So,
right, we got to see that. I hope we have some pictures. I hope you brought.
Well, what we have is we have some artist conceptions that we can share with you.
Too. Yeah,
and,
sure.
so here's again, we're looking at the Trojan asteroids here, but we've got another picture of it up there with an asteroid with rings around it. And the first question is, well, why would an asteroid have rings?
Okay.
Well, maybe a better question is, why do any objects have rings? Okay, so we know Saturn has rings. It turns out that Jupiter, Uranus, and Neptune, all three also have rings. And so any object that's massive enough to pull other objects into orbit around it can in fact have a ring system. But so here we're looking at an artist's conception of this asteroid called Chariklo, and it's got its little ring system there. It turns out that there are 2 rings in this ring system.
Okay.
With the rings very close together. And in fact, they're about 3 miles wide and 7 miles wide respectively, and they're separated by about a 9 mile wide gap. So that's about how big the ring system is. So they're very, very tiny rings. Right. Saturn has a giant ring system. These rings are not very big.
Yeah, and most of and if I've understood that correctly, it's ice and rocks and that kind of material.
We know it is at least around Saturn,
right,
and around the other gas giant planets.
So what about this ring?
So first of all, those things are probably debris left over from some kind of a collision or something that got gravitationally too close to those big giant planets, and those giant planets' gravitational fields pulled them apart. So they're debris fields. Okay, so anything that has enough gravity has the potential for being able to pull in debris close enough to it that debris can't get together and stick together and form a moon, so it just stays in an extended ring. So by that argument, well, maybe Earth has a ring around it. Maybe the moon has a ring around it. How about Mars, Venus, Mercury? It turns out that no ring systems have ever been discovered around the terrestrial planets or any of the larger moons. So it was thought, well, okay, maybe ring systems for dynamic reasons are just reserved for those giant gas giant planets. But now we have a counterexample. Now we have this small little asteroid with a debris field, and here you're seeing what those rings might actually look like from the surface of that asteroid.
Right.
They would be a very sharp, well-defined pair of little thin rings in the sky.
Now I'm assuming that asteroid is large.
It's large, but it's not that big. So it's about 250 kilometers across, something like that. So compared to the Earth, it's tiny. You know, I mean, you wouldn't want it landing on your house, obviously.
No, obviously.
But compared to the Earth, it's a very, very tiny object. Even compared to the Moon, it's tiny.
Must have some kind of core with that gravitational pull to keep those rings.
So certainly it does have a gravitational field. What the scientists are now thinking about this object is, you're looking at the results of a fresh impact. Something must have happened to this asteroid in the relatively recent past that just threw debris out, and we're seeing the remainder of some of that debris that happened to be captured by that asteroid's very tiny gravitational field, and it's still hanging in a ring around that asteroid. This will probably clear out over time.
Okay.
So because of the tiny gravitational field of that asteroid, it's likely that ring will decay over time. It'll either fall to the surface or those particles will escape off into space, but it won't be there for an astronomically long time. It's probably going to fade away, which is why we don't see them around a lot of asteroids. But it just so happens this one's fresh, right? And so apparently these very tiny, small gravitational field objects can have a ring system of their own. They can maintain a ring system for some short period of time. And so scientists will continue to study this object. We don't have pictures as good as those artist conceptions. That's why we don't have a better idea of what this ring system is actually looking like. We only have this occultation data. And I'm sure that scientists will now want to begin to point some large telescopes at this very interesting Centaur asteroid and find out a little bit more about it to see maybe if they can tell how long ago this object was impacted, how fresh that ring system really is. And these are the kinds of observations that they will want to do to follow up to figure out this weird mystery of a ring system around a tiny asteroid right here in our solar system.
It's amazing. You know, I'm always impressed with the notion that they can watch those stars and see very tiny variations in the light or other fields that they're studying and draw those conclusions.
Yeah, that's right.
That is amazing to me.
One of the things I tell my students is that astronomy is an interesting science because it's prejudiced to things that glow in the dark. If things aren't glowing in the dark, we can't really measure them, right? So, and what that really means is an object out there in the universe has to either be making its own light, or it has to be affecting something gravitationally that's making light, or it has to be reflecting light off some other object, or the fourth one is it has to actually move in the way of something that's glowing. And it's that fourth case that we're talking about here, which is an occultation. Something far more distant has to be glowing, making its own light, and this object moves in front of it. And if it does that, then we can make measurements. And so that's what happened at this event. It's that weird science of astronomy, things glowing in the dark out there. All of our information comes to us in the form of light from these distant objects out there, either in the far parts of our solar system or in deep space. And so the science of astronomy and astronomers themselves have to be very good at figuring things out from this information source, which is light coming from these objects in the universe.
Right. I think it's fascinating. And then there's all the darker space. We don't know. Things are happening there too. We just haven't gotten that way to figure that out. But
that's right.
All right, these have been very good stories today for this episode of Twiss. So we talked about, if I got it right, a Carrington-class flare.
Indeed.
2012, July.
Back in July 2012, yep.
Okay, well, we need to watch out for those. That sounds devastating. If it's pointing toward Earth, we're in big trouble. And then asteroids with rings.
Yeah, at least one
planets.
anyway. So
some pretty amazing stories here. All right, ladies and gentlemen, thank you for watching This Week in Space Science. I'm Michael Baltimore. This is Dr. Sean Cruzen. He's a director of the Coca-Cola Space Science Center, ccssc.org on the web. Tune in to Columbus State Television each week and watch Twiss, This Week in Space Science. We'll see you next time.